Okay, so we're going to finish chapter 11 today. I'm ready when you're ready. Yes.
I hear rumors that we're switching from person classes to online classes.
Yeah, there is a big possibility, high probability we're going to do that. So right after class, I'm going to go check how, they are offering different options, different trainings, and we're going to meet for chemistry on Friday to see how we're going to do it. The good thing for you guys, at least you have all the course material, the notes, and the answer key for the problems. There's a lot more on my Canvas than anybody else probably in the department. So that can help if you read the book. But if we're going to go online, I'm going to keep, communicating with you on a regular basis every day during the time of the class. So it's like we're going to get paid, so we have to be there for you for office hours, for all of that. So we're going to see how to best do it, and everything we're going to do will inform you. So you'll be informed by via Canvas. We don't know yet. That's the big thing. So it's weird, like at UCSD, they close the campus but not the labs, which is very strange. If you're not going to allow people to be together, then, why do the lab? You might as well just bring them for lecture. Right. So we don't know what this school is deciding. They didn't make the decision yet, so I can't make any kind of announcement. But some people are thinking to do lab online. I'm like, oh, I don't think so.
Theoretical lab.
Unless I come here and I do the experiment and show it to you. I have to come in person and have maybe a helper.
We have a recording of it so you can see how everything works.
Yeah, so it's like recording it. I don't know. Honestly, I still don't know. We're going to have a big meeting on Friday to talk about all of this. I mean, it's an important thing to think of in the future because this kind of things can happen in many other ways. It can be a virus. It could be any kind of other, issue in the world. Almost feels to me like it's almost like a third world war, biological war or something like that, because everybody's going crazy. I'm not worried at all, but I feel like, it's better to be safe than sorry. Okay, so I'll keep you informed. Whatever happens, we'll let you know. So what we did last time, we talked about organometallics. So I talked about organolithium, organomagnesium, and organocuprates, okay? So what I want to do is to kind of give you what are the advantages and disadvantages, because you have to understand that if you're going to do synthesis, which one is favorable, which one is not. Should I use an organolithium? And mainly I'm talking about coupling, okay? So I'm going to write the reaction for organolithium and organomagnesium and tell you what are the limitations with this. So for organolithium, we start with LiR, and we use R5X to produce R, and that's the coupling. The coupling means you make a new bond between CC, okay, get R prime plus LiX. For organomagnesium, you're going to start with RMgX plus R prime X. Then you get same product, R prime, and MgX. So that's the coupling. Like, how are we attaching two carbons to each other? That's what we call coupling. So what are the advantages and what are the disadvantages? The advantages here we can talk about what doesn't work, but what works really, the advantages is that you can use any R, okay, an R prime. So R and R prime can be primary, secondary, tertiary, you name it. Like any R works it works for all kinds of R's. Okay? But what are the disadvantages then? So the limitations, in other words, what is the limitation? First of all, I already told you that they're extremely what?
Expensive.
They're not expensive, but they're extremely sensitive to water. So we are calling them, they're moisture sensitive. So if it's moisture sensitive, it means you're going to have very, very specific precautions in lab. And that most likely would give you low percent. Okay? Here's the other thing. They are very reactive, okay? So it's good and bad. So both of these, we already established that organolithium and organomagnesium are very reactive. So if there is on the R chain, so if a CO or a CN or a C triple N are on the R, you're going to have competing reactions. So they will react on any double bond, triple bond. Okay? So these are called polar bonds. So these are the polar, multiple bond. These are all polar. And we're going to see this in chapter 16. Yes.
Is that supposed to be an N with a C triple bond? Or is it R?
Sorry, yes, you're right. Talking, writing too fast. It's supposed to be an N. So here, if these are on R or R prime, you're going to have competing reactions. And we're going to study this next. So I'm not worried about it, but it's good to kind of let you know about it. So when we see it again, you kind of understand what I was talking about. So next few chapters, we're going to talk about the compounds with polar CO, CN, C triple N. So we will visit these. So that's the problem with organolithium and organomagnesium. So what is then the other category are the organocuprates, okay? So what are the organocuprates? It's an R2CuLi plus R prime X to produce the coupling. Okay, plus CuR plus LRX. So just like we mentioned about advantages and disadvantages there, first of all, the organocuprates are not very reactive, okay? So these are less reactive. And then, so what are then the advantages? Because they're less reactive, it's basically everything that's bad here is not going to work there. And everything that's bad here is not going to be bad there. And there is a limitation. So here, the advantages is not moisture sensitive, okay? So they're less reactive. So here, they're not moisture sensitive because they're less reactive, okay? So that reactivity makes them less sensitive to the moisture. The other thing is they don't have competing reaction with these. Okay, so if you have any of these, so everything that doesn't work here works here, which is cool. It's a good thing. So if I want something that's not moisture sensitive and that doesn't compete with this reaction, then I'm going to use an organocuprate. So here, they don't react with polar CO, CN, and C triple. So we're gonna put them side by side next chapter. Okay? Another advantage is that you can use them for epoxides. Here, that I didn't mention here. In here, you can't use epoxide. So here, react with epoxide. And when they react with epoxide, they react as a base. So we studied epoxide, how they react with the base. The base attacks these two substituted. So it's exactly like a base. The base would be R minus, that's it. Okay? Now, what are the disadvantages? So here's the problem with them. You can't use any R or R prime. So you have a limit in what type of R and R prime. So R or R prime cannot be secondary or tertiary carbons. That carbon cannot be secondary or tertiary. Why? Because this is very bulky, okay? So if you use something here that's also bulky, the R and the R prime are not gonna touch each other. So that's because of steric hindrance. Is everybody understanding? So if you put very bulky substituents there, it's not gonna work very well. So this is because of steric hindrance. Okay? So this is overall what we studied. So now, what else is there? There are other organometallic, which are the organopalladium complexes. So last type of organometallic we're going to use are the organopalladium. And by the way, all of this is written in the notes. If you really look at the notes, you will see all these details, they're written in there, okay? So what's the next then is organopalladium complex. So organopalladium they're more expensive, of course. Palladium is down there underneath nickel. You know that little bottle catalyst that you used? The good news is only a small amount. I think we paid $500 for a tiny little amount. Yeah. So that's the limitation of these. But the good news is it's only a catalyst. So if it's only a catalyst, you don't need a lot. And, you just need a few milliliters. How much did you use in the lab? How many milliliters?
1.
1 milliliter. So it's not a big deal. It's okay. Now, what are the reactions with organopalladium? We have two of them. We have the Suzuki reaction. And we have the PEG. So you need to know how are they similar, how are they different. Just like I put these here, you see that's a kind of a summary of what you should really retain from the chapter. These organolithium and organomagnesium are very important to make coupling. Same thing here. So what is the limitation for both of them? Both of them, the R must be allylic and benzylic. So for this one, it's benzylic and allylic. For this one, it's only allylic. So I'm going to show you the process, okay? So first of all, if I take overall, let's see the overall for Suzuki. For Suzuki, the overall reaction would be Rx plus L2PD. So that's the palladium complex, and I'll mention what it means. Actually, the overall, I should write it like this. I should put Rx plus B, sorry, R prime, B, OH, OH. It can also be OR, okay? It could be OH or R. something. Could be an alkyl or a hydroxide, okay? So in the book, they just use OR, maybe it's better, so we just, but OH works also, I know for sure. Something else, it doesn't have to be the same alkyl group. So in the presence of palladium, that has two ligands, L2, the coupling is between this R and the R prime. So just like the others, you're gonna have R prime, and then there is a coupling there. And then here, you need OH minus. So you need a base. So why? Because so basically, this bond right here is attached to this one. Okay, so the red stuff becomes one, so you break two to make one. And then what you end up with is the boron prefers the OH to the R, so that's the reason you need an OH minus. Okay? And then that's your reaction, plus X minus. So this is the overall Suzuki reaction. Then, I'll come back. I'm going to leave some space here. And for that reaction, we still use Rx, but here the Rx, the other reactant, is not a boron compound. It's an alkene, and this is what's important. They put it like this. Then you use the same catalyst, but here you have to use a tertiary amine, any tertiary amine. And then this bond here, that's why I put it in red, this bond, and then this bond here, that's why I put it in red, this bond, and here you have, so instead of the H, the H and the R will substitute each other, so you're going to have R, and then this, and then this, and this. So the H leaves, and the R replaces. Of course, you're going to have an HX, which will be neutralized by the So what are the important things to know? First of all, this must be, this particular R must be vinylic or arylic. So what does it mean, vinylic or arylic? And by the way, for both, so it means you have to have something with a double bond or something with a benzene ring which has a double bond. So you have to have a halogen here. Whatever halogen you have, it has to be on a benzene or an array. Okay? Why? Because if you don't have a benzylic or arylic, you're going to have elimination anyway. Okay? So that's the limitation of these two reactions. The best one in terms of choice of R and R prime is this. But this is hard to do. And if you have a double bond, a triple bond, it doesn't work. This one works beautifully, but you have to have an alkyl halide, an alkene halide, or some benzylic halide. It doesn't work with every kind of R or R, so it has to be vinylic or arylic. Yes?
So for the Suzuki reaction, it has to be the R that's with the halogen, not the R with the boron.
Yes. Yeah. Very good question. So basically, It's only that all. Okay? Is everybody understanding now what are the limitations? This is not moisture sensitive. It works no matter what, and you saw it, you added water, you added alcohol, you didn't have to be worried about that. It works beautifully. The only issue is you have to have this or this. But you know, in synthesis, this doesn't hurt. Why? Because once I have this, I attach it, I can reduce it later. So if I want an alkyl group, I don't care. You know, I can start with an allylic and then reduce it. So it's pretty good because a lot of chemicals in pharmaceutical industry, they use Suzuki reaction. That's the reason he got a Nobel Prize not long ago. So this is pretty new. This is in the late 20th century, in the 90s, or it's considered relatively new for science. You know, very, very recent. Okay, any question about the overall reactions? How to recognize the product of a Suzuki or a Heck? Remember, it's the bond that attaches the alkyl to the boron, and then it makes a bond with the alkyl with the halogen. Here, same thing, the halogen, but in this case, it's the H. So you have to have an H. If you don't have an H there, the reaction doesn't work. Is everybody understanding this? So these are the key things. If you need to recognize what is the product, that's what you do. Now, what is the mechanism? The mechanism is not completely understood, so I'll show you how in the book, when you see the big circle and the arrows, I want you to understand how to read it, because eventually, go to the next level, they assume you know that. I tell you, they will assume you understand what that big circle is. So I'm going to take you through the steps of that big circle of the mechanism. Yes?
How is something like this direct reaction discovered?
What?
How is something like this reaction discovered?
Good question. That I don't know. But I tell you, like scientists, what they do sometimes, most of the amazing things, they discover them by mistake or by, just playing with chemicals. They knew organometallic are interesting because I tell you, I started working on organometallic in the 80s. And I come from Africa, and I started working on something that wasn't known in US. They didn't use it. That's how I got a Fulbright to work at Caltech and all these places. But it was just playing with it. I was playing with chromium and put some organic compound with it, and it attached, and I thought, this could lead to something interesting. But then we found that NASA was working on it, and they built most of the space station using the technique that's called Sol-Gel that I was using. So we start with something, and then the next thing you know, you start to read more, and then you start to understand, oh, maybe I should try it here, I should try it there. So people who really get Nobel Prize, they are big readers of science, and they don't just read in their field, they read all kinds of stuff. So that's the reason we receive these magazines. We read a little bit about biology, chemistry, engineering, material science. It's kind of, the more you read, the more you start connecting the dots. So that's how Suzuki probably came up with that. I'm pretty sure that most scientists, that's what they do. Read a lot. If you want to be a real good scientist, you need to read a lot. I don't even sleep, I read more than I sleep, but I read a lot, and I read all kinds of things. But I'm not, the top-notch, like Nobel Prize winner, but still, if you want to be at that level, that's what you need to do. Okay, so let's look at the process, how it works, okay? The reason I like to talk about this process is because it correlates to the concept of Lewis acids and Lewis bases. So it's just to kind of explain again and again that in organic chemistry, if it's not an oxidation or reduction, it is a Lewis acid, Lewis base reaction. It's an acid-base reaction, no matter what. All reactions in organic chemistry, if they're not called oxidation or reduction, they're acid-base. So how does it work? Why the metal? That's the reason I want you to understand. Why do we need the metal? If you understand that, then it's more important than anything else, than understanding the whole idea of the process. So I'm going to start breaking them down one reaction at a time and what they're called, and then put them in that big circle, because you need to be able to, when you see that thing in the book, you need to be able to understand what it means. Okay? So, what is the Suzuki? So we're going to start with Suzuki mechanism. First of all, you have to use your palladium catalyst. Now, what is L? Whenever an organic substituent attaches to a metal, they call it ligand. Okay? Now remember, what is a ligand is any organic chain or anything that's organic with carbon, hydrogen, etc., that attaches to a metal. The minute it attaches to a metal, we don't call it substituent, we call it a ligand. So it's a terminology, but it's not something different. It's not a creature that's new. It's not a new creature. It's just a creature that has now a different name. Okay? So every time you attach something on a metal, somehow people who study this kind of metal, they call it coordination chemistry. They did a little bit of it in 201, and they call them ligands. So in this particular case, what is L for Suzuki? L is really P, phosphorus, and then C6H5. So if I want to draw it for you, it's phosphorus with a benzene ring here, and another benzene ring here, and another benzene ring here. Now you see that this is not convenient to write. You agree? It's too much stuff going on. And of course we have a long pen. So instead of writing all of this, that's what we call F. Okay? So that's F. Everybody understands this? And we don't care really as much as you understand what happens first in terms of our reaction. This is just a catalyst. This is not the main part. So everybody got this? Okay? So first of all, the catalyst doesn't come in the form we want. And in the lab, Mike took care of it. So Mike prepared the catalyst for you. So what does it mean he took care of it? All he does is heat it, and when it's heated, it turns to L3PD until it turns to L2PD. So what happened here? The palladium, it went from 4 ligands to 2 ligands. So it dropped 2 ligands. It let go of 2 of them. And all we need is to do it by heating. Okay? So that's the step 1, is preparing the catalyst. So we go from something very stable to something unstable. So what does it tell us? It tells us now the palladium has 2 empty orbitals. So here it's 1 empty orbital, and then there's 2 empty orbitals. So here is minus L, and this is another L that's gone. Okay, everybody's following me so far? So first step, shake it off, remove 2 of its ligands. Once they're removed, what we do is now we're going to make the palladium now is a definitely very strong Lewis acid. So that's the reason I put the empty orbitals. Okay, so it's definitely here with Lewis acid. And it's a pretty large atom. So what does it mean if it's really large? This is the reason we use palladium, we don't use nickel. You need something huge enough. So when you bring an RX, okay, what it does, it chops this cuts. This cuts. And then R will attach to 1, and X attaches to the other. So basically, palladium is like that big rock that falls into that bond and breaks it in 2, and they both dock into the palladium. So you end up with this, L2, PD, X on one side and the R on the other. So that's really what happened? You create a Lewis acid that has room to attach two new substituents. So the two ligands we had before are now the R and the X.
We have to do the half bar arrows.
No,
No.
no, I'm just kind of explaining like that's basically what's happening. They don't know the exact details, but they know more or less that that's really what happens. Is that somehow the palladium grabs the two. It separates them and grabs the two. Okay, now step 3. So by the way, this step is important to know. This is called oxidative addition. So who's adding what? The palladium is adding the two substituents, and for palladium it got oxidized. So what is the oxidative addition? Who's got oxidized? It's really the palladium. Okay, so the palladium is the one that added, and it's the palladium that added bonds. So every time you add bonds in chemistry, you call it oxidation. Okay. Next step. So now we have palladium holding X and R. The next step, we bring that palladium, and then what happened is there is going to be, that's where you put an OH minus. So here, the OH minus takes, substitutes X. So you end up with L2, PD, and then OH, R, and X minus. So why does this happen? It's less what? Basic or more stable living. Okay? So this is strong base. This is a weak base, which is a good living. So palladium grabs the halogen, and then once you put OH, the palladium will let go of the halogen and grabs the OH. So it's a substitution. Okay, do you see it's a substitution? The X is substituted by OH. Next step, I'm going to write it here, there. So I wanted to write them all together, but that's okay. I don't have, maybe I'll do it. So the next step, you have now L2, PD, then an OH and an R. Okay? So then that's in the step where the boron comes in. So the boron is R prime, B, OR, OR. Now, one thing about boron, it loves OH. Okay? Because it's a Lewis acid. Okay? So this is a Lewis acid. And this is basic. So what it's going to do, it's going to let go of R and take the OH. Okay? So you're going to have an exchange here. So you end up with L2, PD, and then here you're going to have R prime, and here R. And then the boron will take the OH. So there's an exchange between the boron and the palladium. The boron says, please take my R. The palladium says, please take my OH. Okay? What is the last step?
This is the fourth step, right?
Yeah, fourth step. So what is the last step then? What do you think is the last step? The last step, these two come together. Okay? So if these two come together, what do we get? We get back to this. Okay? And this reacts. So the last step, which is step 5, you have L2, PD, R prime, and R. turns into R prime R plus L2 PD. So what is this called? If this is an oxidative addition, what happened to the palladium? Over there, the palladium added the X and the R. And in here, what did the palladium do? It eliminated, so it's in
Reduction.
what's the opposite of oxidation?
Reduction.
And it's in elimination.
Elimination.
So it's a reductive elimination. Okay? And the book explains it clearly, it tells you that if you oxidize and then later you let go, one is an oxidation, the other one is the elimination. So why do you need to know this terminology? Yeah, it's reductive elimination. So why do we need to know this terminology? Is to remember that you always have to get back to that original catalyst, and it helps you remember if I added bonds, I'm oxidizing, I'm reducing bonds, I'm reducing, I'm eliminating versus adding, stuff like that. So this is the overall step by step. Now it doesn't show exactly how the bonds went in and out, and because it's not a very clear, 100% clear mechanism. So how do they write it? So usually they show you something like this. So you start with L4PD, and you have an equilibrium to get L3PD. Let's put it higher. I need more room there, and I can't reach. I'll do like that. You got the idea. So this is L2PD. Now they put a circle. So what does it mean when you see a circle? It means things are coming in and things are coming out, going out. So the L2PD, in here, something attaches, comes in. So what comes in with the L2PD? What was L2PD reacting with? Rx. So you put Rx here. So once we get this, the Rx now is in to produce what?
L2 PD XR.
Mm-hmm.
Call that step oxidative.
Oxidative addition. So this is an oxidative addition. So how do I know it's the addition? You see this is added. So chemists like to kind of do this mechanism like that. If they don't know very well all the details, they kind of say, hey, this is added, and you get this oxidative addition. So what's next?
We have to OH.
So now, OH, so then we bring in what? OH minus, and what happens is you get L2, PD, and then what? OH. So before I write this, something is leaving here. So if you have something leaving, you have to show what's coming in, what's leaving. Okay? If nothing is leaving, you just put one arrow. But in this case, you have this. You have the OH comes in, and what comes out? X minus. Okay? So what we end up with is L2, PD, what? OH, and R. So you see how I'm explaining it? So when you see it, you don't look and see what is this creature. It's weird. Okay, so then what's next? So I already see this is step 1, this is step 2, this is step 3. What is step 3? The boron comes in. So we need to show that the boron comes in. So it's an R prime, P, OR, OR. And when boron comes in, what happens? It comes in as this, it comes out as what? You understand? It comes in one form and it comes out as a OH, B, or, and here, what do we get? We get L2, PD, R, R prime. Are you following me? This is how it came in, this is how it came out. And what comes out of it is this, okay? Then what's the last step? These come together and we get back to this. So what comes out of this is R prime, and the rest. So this is a way to explain to you how to read these diagrams, because I know that when you move to the next level, they assume you know it. You understand it.
Is
Yes.
there like a name for the fourth step?
Which one? This one?
Yes.
I don't know. I don't think so. I think it just, so it tells you here, the catalyst does this, palladium is inserted, the R group is transferred, but they don't give it a name. The only name they talk about are the oxidative
They
addition,
called it
and here is the reductive elimination.
In the
Okay.
lab, it's named transmetallation.
This one? No, that's
Yeah,
not
down.
this.
Yeah.
Transmetallation, when you insert a metal in between two metals. So where is the metal? Where is it written,
In the
transmetallation?
lab.
I
for
don't,
Experiment 4.
I wrote it. I don't remember writing that. I'll double check. Okay, thanks. But it doesn't have a name, that part, I'm pretty sure. I wrote it, so maybe I made a mistake, you know? I'll double check, because I'm the one who wrote that thing. Okay, now, how about Heck reaction? So what's the difference between Suzuki and Heck? Heck uses the same catalyst. So Heck is a little more complicated. And since he piggybacked on Suzuki, he didn't get a Nobel Prize. He improved it for different type of compounds. So, but of course, he's famous. Now his name is on all the textbooks, but probably made some money out of this with a patent or something, but it's not like, you know, Suzuki. Suzuki was the leader in this. Okay, so how does it work? For Heck, the first step is the same. Okay, we're going to prepare the catalyst. The second step is also the same. Okay, so step 1 and 2 are exactly the same. But step 3, we don't have OH minus for Heck. So how do you know it's Heck and not Suzuki? Immediately, you don't have an OH minus. Okay, so for Suzuki, for Heck, there's no OH minus at all. So what comes in here? Is this. You have this thing, the oxidative palladium, now has to bring in the double bond. So we have a C and an H. Actually, I shouldn't write it here, because when I write it kind of like, so here we have an L and an L. I want you to see the two ligands, because now palladium can only have 4 bonds, okay? So if I bring this, and then here H. So here's what happens. The ligand leaves, the pi bond opens. Okay? And then and then this comes in. the alkyl group moves on the pi bond, the empty, because if the pi bond opens, what's happening here? This is positive, you agree? So if this is positive, then you can take the whole R and move it there. So what do we get? We get this. We get still, the palladium will still have 4 bonds. So we have LPD. We still have the X, the halogen. But here, what happened, that L left, so we need another bond here. Okay? So what is in there? It's this C. See how this opens and comes here? I'm sorry, it's this C. So this C has a Z, and maybe there's an H here. So there's an H. Okay? And the other C is right here, and now it has the R. So you see this particular C took the R, and this C attached to the palladium. And then whatever you have here, you have an H and something else.
For the OH substitute the halogen, in this case,
We don't have OH.
I know we don't have it, but we can have some other.
No, not yet. Not in this step. That's what I'm showing here. Yeah, not in this step. So here what happened is, first you create that oxidative, but the second step is one of the ligand leaves, and then the pi bond attaches to the palladium. So it opens up, because it's more sensitive, it's easier to break than bringing OH, okay? So the pi bond opens and becomes a single bond, okay? And you have this, so you have a substituent Z and you have the H. So what you need to know is that this is a syn addition, meaning this bond and this one are on the same side, this and this, okay? So this and this is a syn addition. What I'm talking about is this one and this one. Okay? They have to be on the same side. Then, what's the next step? So step 4, here,
Professor,
yes.
that would be another H, right, on the, where you didn't.
Yeah,
write it?
yeah,
Okay.
I didn't write them, but whatever
Yeah.
it is here, so whatever it is, it could be something else. It's another bond. Okay, whatever it is. So then what is the 4th step? You see, the palladium has all of this. Now the palladium needs to let go of it. That's the reason we put it there. We want the palladium to let go. So in this case, we're going to have a hydride shift. So what they show you is this rotates. Okay? So if it rotates, it's the same as this. So when it rotates, the H will be on this side. Okay? And then you can have an R and this. And at this point, you're going to have a hydride shift. So what does it mean? The hydrogen goes there, and this opens. Okay? So this is hydride shift. So this is step 4. So what do we get? We get LPDXH. And then you have C double bond C. And then you have the Z and the R. So one thing about the double bond, so the Z and the R will be opposite from each other. Okay?
Professor,
Yes.
the rotation, what's the purpose of it if they're so wet?
No, it's still free rotation. So it happens. When the rotation happens, it means to put the H now close to the palladium. That's it.
Oh,
Every time you have a single bond, you have free rotation. So this is a hydride shift and elimination at the same time. Okay? So the H moves to the palladium. That's the reason for Suzuki, for Heck, you have to have this H. This H is important. This H is very important. That's the H. If you don't have an H on your double bond, you can't have Heck reaction. So that's the key part. So of course, we already did the coupling because it's right here. That's your coupling. Coupling happened. So what's then the last step? After you did the coupling, the last step, the ligand here. So this has an H, this leaves, and the ligand comes in. Okay? So the next step is you get L2PD X L2PD, yes, plus HX. Okay? And then the last step is the reason here you have HX, you add the tertiary amine to produce the quaternary amine. So that's why here you have to finalize it with the tertiary amine at the end, just to get it out. Now, you don't need to really memorize all of this, I tell you, but you need to understand what happens. So for Heck, the first step is the same, but here we don't have an OH. So what happens in the second step? What happened in the second step?
Opened up the transition.
So the alkene came. So it's this, H and Z. And then here you end up with, so this leaves an L, the L left, okay? And what you have is X here, and then that thing. And then here, what happened to this one, you have a free rotation, and then the hydride shift. And then you end up with you end up with your product, which is, and then after that, this is the hydrogen and X. Then the last step is you bring, so this gives this, and then you get HX. So then the ligand comes in, and you end up with, actually this is L. Then the ligand comes in, you get this, and then you add CH3, 3N, and you get the salt. Okay? So more or less, that's the ring for that. So all of these are written in your book, you just have to kind of read it, but it's to explain that there is a slight difference between Suzuki and Heck. In Suzuki, you have to put the OH first, and then the boron comes in. In Heck, you put the alkene first, and then the last step is to put the amine. Okay, so all of these are coupling reactions. So what happened next is this chapter talks about two more type of reactions. So we're done with coupling. Coupling means you create a new CC bond. So either you're gonna use the organolithium or magnesium, or organocuprate, or Suzuki, or so all of these are your choices for coupling. So what's left is alkene metathesis. Why they put it in this chapter, it's also because it involves organometallic. So anything that involves organometallic, we're gonna use it in this chapter. So the organometallic here, it's the metathesis uses Grubbs catalyst, which is, what's the catalyst for Grubbs? It's important we know the name. Metathesis. Yeah, ruthenium. So it's ruthenium. Okay, so this is organoruthenium. And I think Grubbs got a Nobel Prize for this because this is super neat. So it's the opposite, it's a coupling, but it's a very special kind of coupling. So what does it do? The ruthenium, you don't need to know the exact formula, but it's organoruthenium. And they're called Grubbs catalyst. So it's a different type of coupling. You have taken CH2, and I use Grubbs. So what it does, it cuts bonds and reattach them. So what happened here, these two break. That's what's powerful, is you break two bonds. Why? Because metals have the capacity, they have empty orbitals. So, and if they're big, like ruthenium, they're gonna grab one from one side, one from the other. But what's interesting is it cuts a pi bond, it cuts a double bond, it produces a double bond. Okay, so we don't need to know the mechanism, but all we need to know is this cuts it in half, and then it allows it to put itself together. So what are the possibilities? Because in half, this is half one, it's the other half two. You see? So when it comes together, it can come back again 1 and 2, or 2 and 1, which gives me the same, or what else can happen? 1 and 1 and 2 and 2. So it gives you two products. So what is 1 and 1? It would be RCH, CRH. So this is the portion 1 and 1. And the other one is CHH, CHH. That's portion 2 and 2. Now what's cool about this type of reactions, especially if you use terminal alkene, terminal alkene means the CH2 is at the end. This compound is a gas. So what happens if it's a gas? It escapes, so it drives the reaction which way? Forward. It's almost a complete reaction. That's what makes it super powerful. So instead of thinking like, how am I going to make a new double bond? All I can do is take a compound with a double bond that I can cut and let it sew it itself in a different position. So, what are the options here? I put this. What is this? I put the cis, but it can also be what? Trans. Okay? So it's not only one, but most likely which one would be the most stable? The trans, of course. For so that's metathesis. Okay? This is called metathesis. Okay? Here's another amazing way of using grubs. You have like a benzene ring, let's say here, and I have a double bond here, and I have a double bond. Let's say I have this. What's going to happen if I put the grubs out?
Close.
It's going to close. So first, we're going to cut this and cut this. And then what happens? This attaches to this, and this carbon attaches to this one. So you end up with this is type of material science stuff, you know. If you go to material science, nowadays they're thinking about making everything at the molecular level. Some of these compounds can have specific properties. So all you have to do is tell this engineer, I want this kind of molecule. How can you make it? And then they have to come up with the design, synthesis, and try it. And that's the future of everything. Future in medicine, future in you name it. It's everything is at the molecular level. And you need to know all these tools. How can I add more bonds? How can I make a double bond in one shot? How can I reduce the chain? How can I add a chain? And that's why organic chemistry, for chemical engineers, the good ones, because there are a lot of chemical engineering programs that are not as good. They don't get you the best jobs because they're not emphasizing organic chem. If you go to any university where organic chem is very important, their chemical engineers, they get very, very high, starting salary is 150,000 with just a bachelor, not even a master's degree. So it's the future. It's not because I'm teaching it, it's because I know how many possible applications you can have with this type of stuff. So this is why you need to know all these tools to know how to put molecules together in synthesis. So when I look at a compound and it says make a ring, maybe this is my best approach, the drug scaffolds. And later I can reduce it, remove the double bond, or I can make more double bonds. So that's another story, like how do we make another ring next? So that's what also chemists can say, okay, I want here conjugated system. And then once you have two benzene ring attached, that's what I worked on. I worked on 19 benzene ring attached. So they look like this, it's a helix. And these type of compounds, they have very high properties, electric properties. They can use them in semiconductors and computers. So start to think about like this benzene ring attaching and attaching, they make a helix. They loop around, and as they loop around, in the middle you have a lot of electron density, and these are like springs. So between this and this, it kind of looks like this, and there are electrons on both sides, so these are good capacitors, because when you push them with your hand, you force the electron to push away. When you let go, they expand. It's like a flexible kind of spring, where you push it down and you let it go. That's what capacitors are. So every time you click on your computer keys, you have something, a capacitor, which is allowing it to be on and off. So you push down, it's on, you take it away, it's off. And then sometimes it's the shape of these molecules that allow you to have these type of capacitors. So I'm just giving you some examples, but I know how amazing these kind of things are. Even if they look hard, they really, it's a lot of separate paths that you can take if you really are good at understanding organic. And I'm done with this. So if you have any questions, let me know. Because what I'm gonna do, I'm gonna go to a meeting to learn how to use certain things on Canvas that I don't know if I learned them, if I know them or not, but I'm just gonna show up. I know it's too early, but we're done with this chapter. I mean,